All right, let's get started. Good morning. I apologize, I forgot to bring the handouts. I took it when I was closing the door, but I don't know where I left it. So it's in my office. I'll bring it next class, or you can drop by and pick it up, right? And I don't have the exam scheduled yet because I'm waiting for some of the people who are still doing the exams. I'm thinking of giving the grades out in class because I think with such a large class, it's going to take me like 10 minutes to hand out each one of those assignments and projects and stuff, right? So you can drop by my office sometime, or we can figure out something else rather than waste the class, right? If you have any problem with that, let me know. But I think this is too big a class to go through this stuff, right? So the homework projects I'm collecting right here. Do you have any questions, concerns with what we've done so far? So we were looking at process scheduling, right? And like most of the stuff, I want you to understand what is it that we do, why we do that, rather than the mechanics of it, right? For example, first come first serve is a simple process, right? And we do that because we don't want to make complicated procedures to do in the dispatcher. We don't want complicated procedures to figure out what should happen, right? And so we choose different policies because of the different metrics we looked at, waiting time and response time and so on and so forth, right? So it's never clear what you should optimize the stuff for, especially since all the goals mean something to the application, not to the operating system. Operating system is trying to manage its resources. So depending on what application you run, you may care about response time, you may care about CPU utilization or what have you. The operating system is trying to guess what it is, right? So one of the constant tensions in this whole world is if the application can tell the operating system what it really wants, right, then perhaps the operating system can do a better job, right? So that the constant argument is if the application tells the operating system exactly what it wants, what it should do, then maybe you can do a better job, right? And the real challenge here is it's very hard for applications to explain what they really want, right? Most of the applications don't understand what is really going on, so they don't really know how to explain what they want. And even if they could, you have to be fair, right? So if you as a PowerPoint say, I want the processor all the time, the operating system has to somehow figure out how to give the process among different applications and what have you, right? So it's a constant battle which is always, it's never clear which way you should go. And one could argue if you're like Microsoft and you write PowerPoint and Windows, then you can kind of have the PowerPoint talk to the operating system and say, I'm PowerPoint, you can trust me because I'm written by the greatest company in the world kind of stuff, right? So they can do a little bit stuff like that. So those are, people can complain it's a good thing or a bad thing, but that's one of the things you can do. The other way you do that is if you buy like a database or one of the machines for doing a specific task. If you're buying a database server or a web server or what have you, right? Those companies work really close with operating system companies to make sure that it's really tuned for that. So if you buy a, say, Oracle server on a real machine, meaning like a couple of $1 million worth of machine, and all it's going to do in life is to run Oracle database, right? Then the operating system company and the database company work together. So they build this database which is really tuned for that particular purpose. You as a customer don't really care because you're paying that much money for the stuff. So that machine may not do anything else well. I mean, your web browsing may be slower, what have you. So that's one way for them to interact well, where the customers don't care, the developers really want it, and the operating system companies want that. But that doesn't happen all the time. So for example, in your laptops, they try to do a good job, and for the most part, they're good. Sometimes they're not good, right? How many of you kind of felt like sometimes the machine is doing something that you really don't want it to do, but you can't just stop it from doing something and do what you wanted? How many of you kind of felt frustration? You remember in what sense? What was it doing that you didn't want it to do? That is one of the most annoying noises that, no, I don't mean you, but like in a conference, right? It's going off and people are like, shut it. I mean, nobody wants to kind of stick out like that, but, right? But Do you guys know why it makes that noise? Why they want to make that noise, other than as a Windows logo, right?
The system's responsive at that point? The system's responsive at that point?
Yeah. Because the operating system hasn't booted yet, so it can't really give you any kind of indication that things are coming along fine. So the only thing you can do is play this music through the sound card. So it's kind of starting, it's coming up, right? So if a machine crashes after that, at least you know that the operating system started to boot. So the firmware gave control to the operating system. Operating system took control. So it's saying, I'm in control. I'm trying to boot, but I can't really talk to you. So the only way I can talk is through like beeps or one of those things which are fairly primitive, right? And so it kind of helps you debug. So if you worked on any machine which needs to be debugged, sometimes you see a blue screen and nothing is happening, right? So you don't know what stage it is, and this is one of the ways where it says I'm in some state, right? So yes, we were talking about some point which you're not pretty happy about and you can really control, right? Anyone wants to take a stab? I saw a lot of people's hands go up. Yes?
Be running one program and have it just take up all the system resources, so when you want to open another one, like nothing happens for a minute or two, and it's just frustrating.
Yeah, that's one of the stuff, right? You have for whatever reason, the operating system has given all the resources to one application, and you want all of it to be diverted to something else, right? And sometimes it's not fast enough because it's doing something that it thinks is the right thing to do, and it gets in your way, and it's a little frustrating, right? And of course, it's all a trade-off. So they could have done it, and if they did something, you may be happy at that moment, but unhappy at another moment. And we'll see throughout the class, some of the decisions that you make would sound fantastic on one scenario, but really awful in another scenario, right? One of the classical things I see is like the advertisements which say, so many of you may notice, we haven't looked at memory management yet, right? But many of you may notice that if you have a Windows machine with 512 megabytes of memory, and you run whatever your program, right? You'll see that you have let's say 10 megabytes of memory free, right? You add a gig of memory, you'll still have this 10 megabytes of memory free, right? And you have 2 gig of memory, you add 4 gig of memory. You throw whatever memory you added, and it still looks like the machine always runs with very little memory left, right? How many of you notice that? And usually there are this little applets or little stuff that people are selling where they say, okay, free up 50% of your memory, right? You run this little application, you'll free up your memory, and after the run the application, you get all the memory free to you, right? You may have seen one of those pop-up ads kind of thing, like pay $10 and we can have this application which will free up the memory, right? Without looking at the memory management, do you think it's a good idea to run such an application? Yes?
Well, if the memory is full of things that would be useful later, that's just like clearing your cache without putting anything in. So maybe it'd be good if you had, you're about to start up one program, like Photoshop or something, that you needed a bunch of memory for, but other than that.
Yeah, operating systems they're much more sophisticated than people give them credit for, right? I mean, they've been doing that for a long while. So they may decide to keep some of the stuff around, using it because they think that you're going to use it again, right? So they may have done studies to show that people typically run Word and Excel and PowerPoint on the machine all the time. So even if you exit out, it's not really exit, it leaves all the state in the system, right? And again, there's a decision which is being made for you because they assume that that's what typical users do, right? So even though it looks like you don't have any memory, that's not a bad thing because it's being used for something else, right? Now, if you are writing a program which is not what you're supposed to do, then of course it's frustrating for you. But for the most part, you should be fine, right? Anyway, so we left off at one of the policies on scheduling, which is the first come, first serve, which is the simplest policies you can think of, right? So there's no decision to be made. It's all in a queue. You take the first one, service it, and then you take the next one, and so on and so forth, right? The decision should be as quick as possible because there's no real decision made, right? But if you could know the future, you could choose processes which are good for you. So if you're looking at throughput, for example, you can look into the future to see the process which will take the least amount of time and sort them based on the amount of time that the process requires, right? And in that way, I can send a lot of processes through the system, right? So in the Gantt chart and all, we kind of mentioned that you have a process and you know how much time it will need. And that's because we're Oracle. We know exactly how much time it needs. But in a real operating system, it does not know. So it gets application. If it can know how much time it will take, then maybe we can do something good, right? So one such application is the shortest job first. And it basically chooses the job with the shortest amount of time required and runs that, right? So there are two variants of that. One is preemptive version and non-preemptive version. In the non-preemptive version, it makes a decision before scheduling a job, and then you live with that, right? So even if a new job comes in which requires a shorter time, you don't change I'll give you examples on the next slide, right? In the preemptive version, every so often, every clock interrupt, you interrupt the process, and then you get to look at then you get to decide which one should take the shortest job first, right? We're not going through the proof of this, but it's optimal for the waiting time. So if you run the shortest job first, you cannot beat that in terms of the time it takes to run a process, right? So it's optimal scheduling algorithm. So we'll see examples of how this turns out. So first is the non-preemptive version. So here, the decision once you schedule a job, you have to wait for it to finish, right? So again, we have the 4 processes. Here, the arrival times and the burst time that the process requires. So you have to choose the shortest job first, right? So over here, process 1 comes in at 0, right? There's only one process, so it gets to run. So it gets to run to completion, right? It gets to run for the next 7 time units. But while it's running, all the P2 and P3 and P4 would have come, right? And then you choose the shortest job first. So you choose P2, sorry, I think it's, there, yeah. So P3 requires 1, and P2 requires 4, and then P4 requires 4, right? Yeah, so that's the burst time and the arrival time. So essentially, you run the stuff and you get the average waiting time, which is 4, right? So in terms of average waiting time, this is the best you could do. And again, if you do a preemptive version, here if you get a new job which requires shorter than what you're currently running, you preempt it to run the other one, right? So again, at the P0, you have P1. So P1 runs for 2 time units, and then P2 comes, right? When P2 comes, P1 requires 5 more units, whereas P2 requires 4. So you get to run 4 up to 2, at which case P2 would require 2 units, P1 requires 1. So you put P1 here, then you let P2 finish, P4, and so on, right? So essentially, you're trying to see how much time is left. So it's not shortest job first; it's shortest time left to complete first, right? And again, the average waiting time is 3. So essentially, this is the best you could do in terms of waiting time, right? And again, you can do this if you knew exactly what the future is. And in most general case operating systems, you don't know, right? There are a class of operating systems called real-time systems. We don't touch upon it in this class. But essentially, those are designed to operate on applications which require specific timing. So for example, if you're running your car, right? Your car has to fire at a certain, the spark plug has to fire at certain exact durations and so on and so forth. So those kind of applications, they're designed where you don't do a best effort. You have to do something at the exact time. If you're running a TV, right, the TV has to be refreshed every 30 seconds. So if you don't do that at 30 seconds, you'll see the screen flickering, right? If you're running a nuclear plant, it has to do certain things at a certain time and so on and so forth, right? So in those kind of applications, you tend to know how much time you would need, right? So because those applications are designed where you fully understand what happens, right? For example, if in a nuclear power plant, if you know that the engineers tell you that for a meltdown after a certain event, right, it will take you 1 second for a plant to melt down unless you stop it, right? You don't run an operating system where you sort of expect it to run for a second, maybe 2 seconds or whatever, right? So you need to analyze it exactly to know how much time each operation will take and whether you can shut it down within that 1 second, because you know that at 1 second there's a catastrophic event. So when you build those operating systems, you know precisely how much each operation would take, because if you don't know the analysis, you're not going to build a power plant. So once you know that analysis, once you know the time, you can feed that time into one of these stuff, so you know exactly what you can schedule. But in real normal operating systems, you don't know. So if you're running a PowerPoint, I have no idea how much time you will need for whatever operation you're going to do, depending on how you interact with it, right? So one way to guess what the future is to look at the past, and that's what we do, right? We kind of look at the past. The assumption here is past will predict the future, right? So the operating system will keep track of something about the past, and it'll use that to predict what the future would be, right? So you can kind of predict. You've been asking for, in the last few cycles, you've been running at 10 milliseconds of CPU. So maybe that's what you'll continue to do, right? That's the logic you use here. When is that logic true and when is the logic not true? When you write a program, right? When you write a C program and stuff, when do you expect this logic to hold, and when do you expect it not to hold? Let's go with when do you expect this procedure to work well? So to make it easy, let me say most of your programs, right, like a simple program, you kind of first do some input-output, right? So you read some data, and then you do a lot of processing, and then let's say you write it out on screen or printer or what have you, right? More complicated programs do different things, but typically you do a lot of little bit of reading, and then you do some kind of computation, then you sort of do some sort of a writing, right? And then you kind of repeat that sort of stuff, right? So when do you expect this prediction to work well? Yes?
You're doing the same thing over and over.
Yes. Yeah, so when you expect the future to be the same thing over and over again, right? So in this sort of program, you sort of expect to do lots of I/O, and then you sort of expect to do lots of computation. You sort of expect a lot of write out, right? So if you think of them as phases, within each phase, you expect them to be the same. So if you're doing the computation, you expect that the computation would, whatever you did in the last slice would be the same in the next slice. When you're switching over from reading to computation, you expect things to change a lot, right? So depending on which phase your program is, it may or may not work out. So in one phase it'll work out well. The transition, it won't work well because it still knows something from the past which is no longer true, right? For the first instructions of the computation, if you look at the past would be reading input-output, which is no longer true, right? So it only works when you're inside a phase. It does not work when you're doing the phase transitions. But of course, operating system has no way of knowing those stuff, right? So that's the challenge. So how far back do you look in the past, right? Because looking back in the past would help you as long as the past does not change, right? So here is let me. So if you look at the three-phase program, right? Like there's a phase 1, let's say phase 2, and phase 3. This is input-output computation, input-output, right? So for example, your slots may have been 2, 1, 2. That's the amount of time you used between doing I/O, and then you do 100, 50, 200. Let's say you do something like this, right? Just for argument's sake, because you're doing a lot of computation, so you want lots of CPU here. You're not doing a lot of computation, so you don't want a lot of CPU, and so on there, right? So if you're looking at the past, right, the real issue is how far back should you look? If you want to look at all of infinity, so over here, at this point, you would sort of, whatever algorithm you run, you will predict that the future will be 1, right? And you're sort of close. and here you'll predict 1.5. If you're looking at the running average, right? So you had 2 and 1, so the next time would be 1 plus 2 by half, so you'll do 1.5. So you sort of, at this point, you sort of have something like around 1 or so, right? When you get here, the prediction would be something like 20 or so, because for once it'll be 1, and then once you add the stuff, your prediction will be very, very bad, right? Till you reach a point where you have enough history, you don't notice the problem, right? Does that make sense? You expect the program to go through these little phases, and how do you know what this boundary is, right? It'll be good if the application can tell the operating system, I'm going to switch over now, forget all the past, I'm going to do in the future. That means you guys, when you program, you have to put little hints that the compiler has to give it to the operating system. And it's very hard. Nobody wants to do that, right? So you have to figure this out. So you don't do this stuff, right? One other way the operating system can do that is it can keep track of all the stuff. You can look at all this history, do a complicated analysis to see where the phase is. It can look, instead of doing average, you can see that it's been going 1, 1, 1, and then it's doing a 10 and 50, do some sort of analysis to see where the trend is and predict what the future is, right? But again, we don't want that, because if the more complicated the algorithm, the more time it takes the dispatcher. So you don't want complicated algorithms. You want to sort of do a little bit addition, subtraction kind of stuff. And the last problem is, the more you have to keep, the more somebody has to keep track. The operating system has to have a data structure to keep track of all the stuff, keep adding and all those things. And you don't want an array for keeping this, because this is all overhead, right? So those are the different parameters which affect you, right? Programs go through these different phases. You don't know when the phase is going to change. You want to look at the past, but you don't want to do like a very complicated analysis. You want as simple as possible. And how do you do that is a challenge that you would have to work out. So one of the common ways you do that is exponentially averaged the past history, right? So you have an equation sort of like this, where alpha is a parameter. You choose alpha for whatever you want, and you look at the next. So this should be +1. The next predicted time slot should be whatever you watched in the previous one times alpha and whatever you predicted in the previous one, right? So you run this algorithm to figure out, essentially the alpha tells you how far back in the future, back in the past you should look at, right? The idea here is if you had some sort of the darker black line, that's the actual observed one, right? So you're trying to develop this blue function which can predict the future, right? So if you run the algorithm, so if this was the actual numbers, your prediction should be sort of close, right? It's close enough that you're kind of okay, but close enough, not complicated enough that you do a couple of multiplication, you're done. You're not doing a very complicated algorithm, right? And the key here is, if you keep alpha to be 0, you don't look at past at all, right? You only use you predict based on just the last number. And if you keep alpha to be 1, recent history does not count if you do alpha is 0. Alpha equals 1, you just look at the recent history, right? So you have to come up with this one magic number which tells you how far back you should look at, right? Equation is not complicated, but the more you look in the past, the better you can be if you're within a phase, but the worse you will be when you're switching phases, right? So if you look too much into the past, then it'll take you a while to switch when you switch the phases. So you come up with some number, and right, which will be good for you, right? Again, this is one of the magic numbers that all the operating system companies have to figure out what is a good number for a different operating system, right? So so they may change it across operating system version. So Windows XP may have used a number, Windows system may use a different number. They may switch it across the different, like server or desktop or whatever version they have, right? But anyway, by changing this one number alpha, it tells you how far back you can look at, and if your application tends to match what this was trying to do, you'll work out fine, right? So which also means that when you're developing a program, right, if you're developing a program but you want to get the last bit of performance out of the system, you have to be aware of how exactly this is being done, right? So in which case you may be able to change your program such that you don't go through abrupt changes, right? Because if you as a programmer wrote a program which is fighting with what the operating system is trying to do, then you would lose because you're not going to get the right amount of stuff. Does that make sense? If it expects that you will you'll do the phase transition slowly because you're looking at the past, right? I would not write a program where it goes 1, 1, 1, 1,000, 1,000, 1,000, 1, 1, 1 kind of stuff. Because when you go into 1,000, it's going to give you 10 or so milliseconds. You have to keep lots of context switches and it'll be slow, right? So thinking of context switches and stuff, for the homework project 1, right? How many of you actually noticed a big significant difference when you change the clock cycles and stuff? How many of you didn't notice any difference? It has to be only 1 or 2, right? Small, huh?
Yeah, it was really small for us.
Yeah, I suspect it's small. So, any theories on why it's small? I think you guys should have gotten small differences, right? Because it's very hard to, especially when you're going from 100 to 1,000, right? Yeah.
It's kind of actually a small program. Shouldn't take too long to run, so there shouldn't be too many other interrupts running from others. There shouldn't be too much process sharing.
Yeah, I think the machines are too fast. I mean, it's really fast that the overhead is relatively small, right? And yeah, if you're doing some real application, it'll make a difference. But for this toy application, you're probably not stressing the machine enough to make such a big difference, right? So for the most part, if you're writing a program for any programming class or something, you don't have to be super optimal. The machines are fast enough that you're kind of okay, right? But if you're doing this for like scientific and computing kind of applications, you really care. Like some of the folks in the department are working on solving biology problems and stuff. And those applications run for weeks and months, right? So difference of an hour or 2 hours in a month run, it's still a big deal. I mean, it's still, you save a few hours or so, right? But for that little thing, it's surprising that you even notice a little difference because the machines are fast enough, right? So that's one of the things that you have to be aware, and most of you are probably aware of it, right? You don't have. So back in the days, people used to program in assembly language or C, being super optimal about every little things. But I think these days you can sort of be okay, and your programs will be fine. And this is one of the things you see that, right? So it is still important to worry about those stuff, about how it happens, and especially when you're writing programs which are important. Toy applications, you probably are okay, right? So that's one of the class applications where if I can predict the future, I can do a good job, and you predict the future by looking at the past, and that's used all over the operating system, and we'll see it over and over again when we look at other stuff. You try to predict what the future is based on the past, and if the past is a good indicator of the future, you win. Otherwise, you lose. Why you should care is you're going to use the operating system. So if the operating system is doing a certain way, you as application programmer should work with it. If you're trying to fight with it, then you will lose because it's not going to give you the right performance, right? So the next model of scheduling is called priority scheduling, right? Where it does not matter when you come in, depending on what your priority number is, I'd let you go somewhere, right? So if you're a high priority task, you get to go first, right? And you can have a preemptive and non-preemptive. In the preemptive version, if a higher priority task comes in, yours will stop, and only that will get running, right? How would you assign the priorities of these tasks? If you could give a priority, which one would you give priority in your, say, your desktop? If you're, let's say you're using PowerPoint, right, and you're doing something, which one would you give priority? Let's say you're using PowerPoint and there's an Internet Explorer on the background, and then there's a printer or something in the background, right?
The one that you're using, like for PowerPoint, if you're using PowerPoint, you want that to have the most.
Yeah, you would like to give something that you're using higher priority, right? Where it gets tricky is you may be using other stuff that you don't really know, right? So for example, you may be using a printer, right? So if you give all the priority to PowerPoint, the PowerPoint is trying to print something, you have a priority inversion problem. No, you have a problem where the higher priority is going to starve the lower priority, right? Priority inversion comes later. So, the idea here is PowerPoint has so much priority, you cannot let the printer run unless it stops itself, right? Because if you're going strictly by priority, I have the highest priority, so even though I want the printer to run, I cannot make it run unless I give my higher priority from PowerPoint to the printer, right? So strictly priority-based systems work well if you know how to manage the priorities very well, and you don't hog up the priority a lot, right? You never want to give high priority to a CPU-bound task, right? So one of the ways you can, so what you do is you age the priority. So even if you do give you high priority, I age it out because I kind of say, I look at how much CPU you've been using. If you use a lot of CPU, I will age you out just because it's fair, right? Just because you think it's a good thing to do, right? You don't try to do this for real-time systems because real-time systems, you expect them to know what they're doing. If you want to know what will happen when you run with a higher priority, write a program with the infinite loop, right? Make it into a real-time task. You can do that with, like if you're using Windows, you go to Task Manager, make that process into a high priority task, make it into a real-time task, right? Keep it the highest priority, give infinite loop, right? Make sure you save all your stuff before you do this stuff, right? Because if you're running on only one processor, like not a dual core but a single processor machine, that task will have all the priority, right? You won't be able to get in and kill it or whatever because you all have lower priority. So unless the task manager or whatever has higher priority than your program, right, you won't be able to do anything because it has all the priority. So till it stops, you're not going to get control. And if you're just going in a while loop, it's again one beautiful way the machine will crash, where machine will be working fine for that particular task, right? Nobody else can do anything. You just sit it out, right? So if you want to try it, go while for a large number, and then it exits out, kind of thing, right? And if you try that, you'll see that when it's running in a higher priority, you can't do anything, right? Which is a good thing for certain kinds of operations, but a bad thing for certain kind of operations, right? It's a good thing, especially when you know what you're doing. It's a good thing when you're watching something like movies. Like how many of you, if you watch a movie on a DVD or so on the computer, and if you don't have a hardware DVD player on the stuff, right, you'll notice that it'll kind of keep stopping whenever somebody is doing something else. You wish you can give it a higher priority where the movie will run continuously. But if you make a DVD player into a real-time high priority task, then you can't do anything else till the movie kind of finishes because it's running at high priority, right? So the challenge is how to figure out which one should have the high priority, how to move it and stuff. In regular systems, you kind of age it out. But there are scenarios where you don't want that. You want the highest priority to be given to this particular task. So that's one way of scheduling. You get full control, and if you're not careful, you lose all the, you get what you wanted, right? And the last one is the round robin, which is a variant of the first come, first serve, right? This is a preemptive first come, first serve, is essentially round robin. Here, it's first come, first serve for a given time slot. So I give you the time, the way you schedule for the homework project 1. So let's say I give you 10 milliseconds. After 10 milliseconds, I choose the next one from the queue, next one from the queue, next one from the queue. And after the 10 milliseconds, I put you on the back of the queue, right? It's a first come, first serve, but you get preempted after the time clock. So I keep switching back and forth, which is sort of what you would have seen in the program you're running. So instead of you running all the time, I let you run for whatever hertz you set up for your project. And after it's done, I move you to the back, bring the next one, and then next one, and so on and so forth, right? So round robin is a good function, and depending on how much clock cycle I assign to you, you get that much CPU. If I make it very small, then I switch this often, so everybody gets somewhat of a share. If I give it for a large amount, then when you're on, you expect to run for a while. So that's what you were trying to see for the homework project, right? And as you notice, if the machine is really fast and the program is not that beefy, then you may not notice a big difference. So essentially, the idea here, if you look at the if you look at a time quantum of 20 and you have these different processes with a different time cycle, so you run basically P1, P2, P3, P4, but after 20, you yank the P1, right? And then you move P2, it only requires 17, you run for 17. Then you take the next one, give it 20, and so on and so forth. So regardless of what schedule, you still take the same amount of time, but everyone is more responsive because they keep getting some amount of clock cycles, right? And depending on how big the number is, you will avoid the context switches. So if you have a really large quantum, then you don't see any, it becomes a first come first serve, right? And as you reduce it, you have more context switches. So the challenge is to come up with a context switch number which you can live with, right? So it's a variant of the first come first serve, which is preemptive, right? And so the average turnaround time depends on the amount of quanta that you gave to the application. So in real operating system, one of the things we mentioned was you never know what is good. You can't come up with one scheduling policy which is good for everyone. So most real operating systems these days have multi-level queues, right? So they have different queues with different scheduling algorithms. So a process can be in various different states. So they may call this as different classes. So they can say we have scheduling one for interactive jobs, one for normal jobs, one for real-time jobs, one for background jobs. So they call this different names. And within each class, they can do a different algorithm, right, with different time quanta. The hope is when you run your program, you'll put your program into the right slot where you get good performance. So if you're running an interactive job, you'll put yourself into the interactive class, and the operating system can give you a good job, good behavior, right? So this is sort of how you set it up, and you put I think the book has the student processors at the bottommost tier, right? But essentially, you create these kind of classes, and you run different algorithms in each class, right? So when a new job comes into the system, you have to put it into one of these classes, and you can run a different algorithm in each one of those classes. And you also age it out. So you kind of assume, if you assume that if you're higher up, you get more priority. If you're lower up, you get lower priority. Then it may age out to the bottom. So there's a complex behavior of how these things keep turning around. So in a normal machine, even though you may see classes of, if you look at the process state, you see different classes and stuff, but they're constantly aging themselves out. So you don't get exactly the precise behavior you want, but you sort of get average good behavior, whatever the developer wanted you to have, right? And so now the parameter for a system is how many queues you have. The more queues you have, the more finer grained you can manage. But it also means that if you have lots of levels of queues, then the operating system becomes complicated, right? So when you run the dispatcher now, it has to keep track of which process to take from among the levels and which process to take from within the level. So I have to select that. So I may have to decide that 50% of the time I will give it to the first level, then 20% to the next level, and so on and so forth. And then within each level, I have to keep track of which process is in that level. So the more levels and more scheduling algorithms, it becomes more complicated, right? And so you try to strike a balance where you have the right number of levels, right number of queues. And so the scheduler now has to do both the stuff, which class and which process, right? And one of the example, for example, is you can have the Q0 is a round robin with a quantum of 8, Q1 is a round robin of 16, and the last one is a first come first serve, right? So you assume the Q0 is one which is higher priority interactive task, and Q2 is something low background task which doesn't have to be, which can run for all you want. So essentially, you kind of move it into the first class. If it seems to take more CPU cycles, you move it down to the next class and move it down to the next class. So interactive jobs would be on the Q0 level, where the time quanta is so small that you can run a round robin, give good response time. But if you're taking too much CPU time, it downgrades you to the next level, and so on and so forth. So that's one way where your behavior changes with time depending on how good or how bad you are, right? And this is the example of how that might look like. So again, the things to keep remember is there's so many constraints on what a scheduler can do, right? In terms of it has to be simple, it has to be fast and stuff. You don't have too many choices, right? But the key point to remember is you're trying to figure out what is a good schedule for the future. You're never going to be accurate, but you hope that your experience gives you, it tells you what number is good for you, right? For example, like 8 or 16 or some number based on what you expect processes to be created, what's the typical duration, all those things. And for the most part, machines are good, except the times when they're not good, right? And you as a developer has to understand all this stuff because you have to figure out how to do this stuff, right? As one of the examples, you can look at operating system that you're using and look at the different processor classes there, right? And trying to figure out where you should put your PowerPoint or printer, it's not as simple as you imagine. And the operating system tries to make sure that you don't shoot yourself in the foot by aging stuff. So you can put it in one queue, but it still will go down to a different queue or what have you, right? So this is all for single processor, right? When you go for the multiple processors, you have other issues. Right? Some things become easier, right? If you have two processors or like 4 or 5 processors or large number of processors, right? Because in the future is towards multiple processors, right? I think Intel wants to go to 40 or 80 cores per processor because of the way hardware restrictions are. So when they go to more processor, when you have a lot more processors, so in some sense you don't have to be so precise, right? So if I have 2 processors, I can afford to leave one of the processors on one processor just because if I believe that you only need, like say, 2 more time units, right? If I have to be fair, I have to kick you out, but I have another processor, right? So I can be kind of nice to you. I can give you that extra 2 kind of stuff. So when you have multiple processors, operating system can afford to be a little bit lenient with you because you have other stuff to manage, right? So that's the good thing. The bad part is there may be applications which want all the processors to do different stuff, right? If you have running a threaded application, you may want to use all the processors. So for those applications, there has to be a way to give you as many processors as you want, right? And one of the ways to do that is called gang scheduling. But essentially here you can say, my application, I know there are 8 processors in the machine. I want 4 processors to run, right? Because I have a multi-threaded application. I work well when I have 4 processors where I can schedule my thread, right? So do not schedule me unless you can give me 4, right? If you can give me 4, I want all 4 at once, and I want to be able to manage it. But if you can only give me 3, don't run me at all, right? Those are complicated in some sense. Those are wasteful in some sense because you have to give all the 4 to one process. But you try to work with that because these are different class of applications, right? The first generation of operating system, when they come out with this stuff, we'll see in the next module notion of synchronization, right? When we looked at the threads, we saw threads running around and doing stuff whatever they want, but if they're operating on the same shared data, you have to be clear on in what order they work and stuff like that. And that means you need to have things called locks and semaphores, right? And we'll see that in the next module. Those tend to be pretty hard to work, right, to make these things happen. In the first generation of operating systems, the operating system itself is not thread aware, does not do locking properly and stuff. So in those systems, they'll have asymmetric multiprocessing, where they say operating system will only run on one processor, So if you're running on an application on any of the different processors, any number, if you make a system call, that system call can only be serviced on this particular processor, right? It's not a good thing, but it makes your development cycle easier. Most of the current operating systems are truly multi-threaded, so they can run on any of the systems, right? What that means is if you have a lot of system calls, then you may have to go to this one processor, right? But if you have symmetric multiprocessing, any thread can do can operate on any of the processors, right? So gang scheduling is one of the important stuff, and how to manage this stuff. So it's sort of easy. So if you have one processor, you have to be pretty careful on what you give, because if you give it to the wrong process, nobody else can make progress. And then when you increase the processors, you get a little bit more leeway. You can kind of afford to give you 4, even though that may be unfair to the rest of the system because I have more. Once you go beyond a certain limit, then again it becomes a problematic. We're not going to touch that, right? So if you have like 1,000 processors or 10,000 processors, right? Then I have enough processors, so I can be completely free. I can say all the processors get a processor, right? But gang scheduling with 1,000 processors is very hard, right? If you want an application which wants 4,000 processors, then the operating system issues with that becomes very hard. And we won't touch on it because it gets into high performance computing kind of stuff, but that's one of the challenges. That's one of the reasons why you don't just build a supercomputer by adding more processors, right? The more processors you have, the management of how to keep them all scheduled it's not a trivial task, right? So I kind of mentioned a little bit about the real-time task. There's two notions, hard and soft real-time. What you need to know is these are considered to be so important that you expect, so you know how much each these applications would require. The application developer would know precisely what they require, and they will somehow tell the operating system that I only want so much stuff, and they are fine, right? So if you're running a DVD player can say, to decode the next frame, I take 10 milliseconds. So I want 10 milliseconds every so often kind of thing, right? So if you upgrade a process which is not real-time aware, which you can do in most machines, then you have catastrophic results. So if you take a PowerPoint and just assign it to a real-time queue, which you can do it in the task manager, if you do that, you'll notice your machine does not do what it's supposed to do. But for the class of application they're trying to do, this is a good thing, right? We're not going to go through too much of that because there's actually a senior level course called real-time systems where you go through this for the whole semester, right? And the last one is the notion of the thread scheduling, right? So the thread scheduling, there's 2 levels of scheduling, one within a process and one across the kernel, right? So how do you decide within your application level library which of the user level thread should be scheduled to a particular kernel level thread is issue 1. And within the kernel, which of the kernel threads should be assigned to you, or how should that scheduling happen, right? It's easy in systems like Linux because it only has one concept. It has a task, which is sort of like a thread kind of stuff. But if you have an operating system which has 2 concepts, process and threads, you have to figure out how to do which scheduling, right? The issue here is of fairness, right? So if you had a concept of a process and a thread, and one process was asking for 1 kernel thread, and another process was asking for 2 kernel threads. If I treat them all, if I was not aware of this difference, right? If I give each of them 1/3 of the time, so the process is getting 1/3, the threads are getting 2/3, right? Which may be good, which may be unfair. You have to figure out what to do, right? So that's one of the challenges you have to deal with. If you don't care, that's fine. But if you care, you would like to give each of them half the time. But this is only asking for 1 kernel thread. This is 2 kernel threads for 2 processes. How do you manage those, right? I'll stop with this and continue on in the next lecture.